This is a video tutorial for the Unit 2 take-home test. This is what should be completed in preparation for your exam. The exam is Wednesday the 28th for red day and Thursday the 29th for blue day. Okay? So this is the tutorial key. The things in pink are already keyed for you. The things that I have highlighted in green we're going to do together on this video. And the things that are highlighted in yellow I'm not going to do for you. I'm going to expect you to have done when you turn this in. Okay. Make sure you get your name and your class period on this so that it gets graded well. Now this take-home test is a quiz grade. It's a version of the test, which is why we're giving it to you as a take-home test. Right. This first section, there are a lot of knowledge-based questions that come from this first section. Probably 4 or 5 questions on the exam are represented right here. So please make sure that you're not treating this lightly because it's just fill-in-the-blank notes. The arrangement of electrons in the atom is the configuration. So when we're getting to something down here like this, 1s2, 2s2, 2p4, that's oxygen's 8 electrons, 2 plus 2 plus 4, 8. That's where they are arranged. The arrangement of electrons is the electron configuration. Electrons fill up the lowest energy levels first. You go low energy to high energy, just like we would do. We would choose to take a nap in chemistry rather than do some homework in chemistry. We're low energy first, just like electrons. The lowest energy state of the electron is called the ground state. According to the Pauli exclusion principle, 2 electrons can share an orbital, but they have to have opposite spins. Alright, opposite. And opposite spins, we're talking about up-down arrows when we draw them as orbital notation. Up-down arrows. So let's see what we've done. We've gotten configuration, we've gotten ground, we've gotten lowest, we've gotten opposite. An atom's blank is a measure of how much it wants additional electrons. I'm going to circle that on mine, wanting more electrons. Let's keep reading though. The blank energy is the amount of attraction you have for your own electrons. Okay? So one of them is wanting more electrons, and one of them is wanting to hold on to the ones you already have. So wanting additional electrons, this first one, is electronegativity. Okay. Now electronegativity, if you look at your periodic trend summary on the periodic table we gave you, remember for electronegativity right here, it stops at fluorine. The noble gases have a very, 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 very low electronegativity, almost no electronegativity, because they don't want additional electrons. So that's how you can remember. Wanting additional stops here because they want one more, but they want no more, so they have no electronegativity. But the noble gases do have a very high ionization energy because that's how attracted they are to their current electrons. Okay, so ionization energy, this next one. Ionization energy is the amount of attraction you have for your own electrons. So noble gases have such a high ionization energy because they don't want to lose the electrons they already have. They already have 8 valence electrons. So they have low electronegativity, noble gases do. They have very high ionization energy. They don't want to lose electrons, they don't want to gain electrons, electronegativity, but they also don't want to lose electrons, ionization energy. Please make sure that you go back and rewind that and look at your periodic table, push pause, and really make sure that you know the difference between electronegativity and ionization energy. The atomic radius, alright, so we're here. The atomic radius measures the size of an atom. So we're talking about the distance between the nucleus and the outside of an atom, alright, right there. The center of a circle, just the outside of the circle, that's the radius. So the size of your atom is the atomic radius. And the blank uncertainty principle, you should know that. And it says that you cannot know the position and momentum of an electron at the same time. Alright. Write the electron configuration. I'm not going to do iron for you. I did do oxygen, so my expectation is you have done this and you're just checking your answer on oxygen. So we come up and look at calcium. Calcium is Ca. It has a total of 20 electrons. So the electron configuration is then where are those 20 electrons? So I very, very, very strongly recommend that you rip up 2 little pieces of paper and put one on calcium. The 20th electron is calcium. And we can pretend like the other elements in the periodic table are electrons. So electron 1, electron 2, electron 3, 4. Okay? So I'm going to pull this up so we can see calcium here and the periodic table. Let me see if I can just zoom out a hair more, or we can get it in there. Perfect. All right. So calcium's first electron is at 1s1, and I go until I get to the end of a block. So the end of the s block is right here. So I would stop and write 1s2, because it's 1s2. After electron 2, we go to electron 3, and go to the end of the block, which will be 2s2. After electron 4, which is where I am, I have to go to electron 5. And I'm going to keep going till the end of the p block, which is 2p6. After electron 10, we go to electron 11 and drive to the end of the block, which is 3s2. After electron 12, we go to electron 13. And at the end of the p block, right, we just go all the way to the end of the p block, we've got 6 electrons and 3p, so 3p6. And after electron 18, we go here, and then, oh look, we're at calcium, which is 4s2. Okay, so if we add this up, 2 plus 2 plus 6 plus 2 plus 6 plus 2, that's 20. That's where calcium's 20 electrons are. So again, electron configuration is the arrangement of electrons in an atom. Coming down then for noble gas notation, it's a shortcut. It's the exact same thing, but it's a shortcut. Here you can check nitrogen's noble gas notation. Now remember, even though it's written right here, okay, I had my students kind of go like this on their periodic tables. Helium is a noble gas. So look at this side of the periodic table. Helium's written right there in the noble gases because it doesn't want any more electrons. It only wants 2, which is why it's here as well. So in getting to nitrogen, the last noble gas I passed through was helium. So after helium was 1s2. Wow, excuse me. 1s2, I'm glad I said that. And then 2p3, because nitrogen is at 2p3. Sulfur, I'm going to go ahead and put one of my electron, or my markers there. And then instead of starting at electron 1, like I did up here for electron configuration, I can start at the last castle I drove by. The last nobility lives in the castles, right? So on my way to sulfur, I drove through helium as a noble gas. Yeah. And I drove through neon as a noble gas. And I haven't gotten to argon yet. So the last noble gas that I passed through on my way to sulfur was neon. So we can use that as a shortcut. Instead of giving directions from your home, you're giving directions from that castle. So hey, y'all know where neon lives, right? Right. Start at neon's house, and after neon, which has 10 electrons, we go to electron 11. So we're starting here at 3s and drive to the end of the block. So 3s2. Alright, after electron 12, we go to electron 13, and we don't go to the end of the block, so we get to sulfur. So sulfur is at 3p4. And there we are. So there's the shortcut for sulfur, the noble gas notation. All 3 of these will be on the test: electron configuration, noble gas notation, and orbital notation. Okay, again, there's your answer for lithium. Go ahead and check your work. Lithium has 3 electrons. Okay, number 3 on the periodic table. 2 of them, 1, 2, are in 1s, and 1 of them is in 2s. So we draw a single up arrow. For sodium, I'm going to do the same process. Alright, I start with electron 1. My first 2 electrons are in the 1s orbital. I'm going to write 1s, and then we've got s, p, d, and f orbitals. Those are different orbitals, sublevels that we have. And then we can count by odd numbers: 1, 3, 5, 7. So anytime I write the letter s, even though that looks like the number 5, anytime I write the letter, that's worse, s, sorry y'all, it has 1 orbital after it. Anytime I write the letter P, I have to put 3 orbitals. Letter D, 1, 2, 3, 4, 5 orbitals. 1, 2, 3, 4, 5, 6, 7 orbitals. Alright? So sodium, 1s, and there are 2 electrons in there. So just like I wrote 1s2 up here, and that little 2 represented 2 electrons, here my 2 arrows represent 2 electrons. Now if you're not in my class, I do half arrows, that's how I was taught. It's faster. Do the full arrow or the half arrow, it really doesn't matter. After electron 2, we go to electron 3, which is in the 2s orbital. I put 2s, and since I wrote the letter S, it gets a one-bedroom house. It gets one orbital. And there's 2 electrons in it, so up, down. That's where those electrons 3 and 4 are. Then we go to electron 5 over here, so I need to put 2p6 on there. 2p, anytime I write the letter p, I get 3 orbitals. 1, 2, 3, and there's 6 electrons. So I go up, up, up. Electrons all have to have their own room. That's the Pauli exclusion principle, that you have your own room first. Every electron gets its own room. I told my students every student gets their own piece of pizza before you start sharing. Then we will go down, down, down. Actually, that's the Hund rule now that I'm remembering it. After electron 10, we go to 11. So sodium is in 3s1. So we would go 3s. S orbitals always have, or S sublevels, have one orbital. And 3s1 would just have one electron in it. Go ahead and do the same thing for phosphorus. That's that same process. And there's no shortcut. You can't start at a noble gas. You start at 1s. Okay. Coming down here now. You can check your work for number 5, noble gas notation for nickel. I crossed out these two because nickel and I has not gotten to krypton yet. So there's no way that's the right answer. That's why I just went ahead and crossed them out so I kept track. There's your right answer. What's the noble gas notation for yttrium? You're going to do that on your own the same way you do number 5. Number 7. What orbital is the last valence electron of vanadium in? Vanadium's right here. Number 23, capital V, vanadium. If you did not know that, you could look on this side of the periodic table and find the name vanadium is V. Okay. But vanadium is in 3d3 if we're graphing that point. So 3d3 right there. A lot of times people want to say 4d3 because it's 4s. 4s, but this says 3d. 3d3, not 4d3. Okay. Question 8 is the correct electron configuration for chlorine. First we got to find chlorine. Chlorine is in 3p5. So it's not in 3p1, that's not it. 3p5 right there, yep. 3p6, no. 4p5, no. 3p5. Now I'm going to go back and check. 1s2, 2s2, 2p6, 3s2, 3p5. That looks great. If there was something weird in here, like a 4d or a 2s7, I would know that that can't be the right answer. So I went back and checked my work. I'm all right. Number 9, do not switch this. Remember that a group, and I'm about to switch it right there as I'm going too fast here. So let me get my whiteout and fix that for y'all. But remember the difference between groups and periods. All right? A group is vertical like that. A column, group, or family. A period is horizontal. Just like you write a sentence and put a period at the end. That's horizontal. So the element 3p1 is aluminum. Can we find that? 3p1. So it's asking me, I'm going to scoot that right there, what group and period aluminum is in. So I'm going to turn my periodic table over and see that aluminum is in group 13. You could also call it group 3A. You could not just say 3, but group 13 or 3A. And aluminum is in period 3. So group, period. All right, go ahead and do that same process for number 10. Let's turn, actually, I'm going to ask you to do me a favor. If you were watching this video on your homework, please draw a box around page 1 and say that you checked the video and draw a smiley face there. That way when your teacher grades your homework packet, your take-home test, we're going to know if you're watching this video or not. Okay, so go ahead and do that. Okay, on the back, I'm going to ask you to do number 11 on your own. Find the electron configuration for this element. It's asking you to identify what elements that is. You should be able to do that from what we've already learned. All right. The electron configuration notation for blank, what elements, is 1s2, 2s1. So that's 2 plus 1, 3 electrons. And the element in 2s S1 is lithium. Li, lithium. Neon is over here in 2p6, so it's not neon. Hydrogen is in 1s1. Beryllium is in 2s2, so it's lithium. Which of the following breaks Aufbau's principle? I told my students you don't have to memorize Aufbau's principle. You don't need to know that guy's name in order to know that one of these is wrong. So 3 of these are correct, 1 of them is wrong. Which one is breaking a rule? Even if you don't know Aufbau's principle, you can still answer this question. So let's look. 1s2, 2s2, 2p6, 3s2, 3p5. That looks okay. So I'm just going to kind of go like this. That one looks okay. B. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, the only difference is that's 3p5, that's 3p6, but that looks okay. C. 1s2, 2s2, 2p2, 3s2, 3p4. That does not look right to me, so I'm going to circle that and be like, something suspect here. D. 1s2, 2s2, 2p6, 3s2, 3p6. In fact, these two are the exact same. That's a typo. It shouldn't be the exact same, but that one's okay. So A, B, and D all look right. That's a problem, because p electrons can hold a total of 6, or p orbitals can hold a total of 6 electrons. So this isn't full. So that is breaking a rule. In fact, it's breaking Aufbau's rule, which says you fill up low energy to high energy. This isn't full. You would never put electrons in the ground state into this orbital unless that one's full. So 13's wrong. Do the same process for number, that's really funny, there's 3 of the exact same answer. Darn it. For number 14, okay? Go ahead and do that. And I switched those on you. Okay, do number 14 the same way. For number 15, it's asking you what element is this orbital notation. And you can count up all of the arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 arrows means 13 electrons, which means aluminum. That looks like Be, but it's 13 electrons. Or you could say there's 3p1, and 3p1 is aluminum, but it's definitely aluminum, Al. Number 16. This orbital notation correctly represents valence electrons only. So what group is this valence electron? So remember, we have a total of 2 electrons that can fit in s orbitals, 6 electrons that can fit in p's. 2 plus 6 equals 8 valence electrons. So there's my octet. This is an octet rule. So this group only has 3 of the 8 valence electrons. So what group has 3 valence electrons? We don't worry about the B's. The B's are the bad boys which break. Okay, the B's are the bad boys which break the octet rule. The A's up here always keep the octet rule. So 3A has 3 valence electrons, or group 13. So you can say group 13 or 3A. Do not say group 3, because that would be 3B. That's group 3, and that's not it. So any of these elements, boron, aluminum, gallium, indium, thallium, they all have 3 valence electrons and would look like that. Number 17, you can check your answer. Again, it's group 17 because there's 1, 2, 3, 4, 5, 6, 7 valence electrons. So 17 or 7A would look like this. Go ahead and do number 18. It should look really familiar to you. Number 19 is the same thing. You should be able to answer that one on your own by now. Number 20, what orbital is the last valence electron of gold in? Biggest thing is you need to know what element gold is, and that it's Au, not Ag. But gold is Au, and it is in 5d9. Okay, gold, right there. 5d9. There's your answer. You can check your work for krypton over here. Okay, 4p6. Go ahead and do titanium all by yourself then. Make sure you're doing Ti for titanium, not Tl for thallium. Number 23, they're talking about atomic radius. Remember, atomic radius is the volume, basically, of your atom. Radius, from the center, from the nucleus, to the outermost valence electrons. So you're going to want your periodic trend summary side in order to complete this. Let me see if I can get that to work a little bit better. So if I'm looking at this, and I very, very strongly recommend that students on your test, just go ahead and rip up a little piece of paper, the corner of your test. Okay, but let's take a look. So, I've got sodium. I'm going to mark that. Sodium. Na. Cesium. Cs. I'm going to go ahead and mark that right there. Lithium. Li. Okay, and then potassium. K. Right there. So it's asking you to put those 4 elements in order from smallest to largest. And remember, that's the less than sign. The alligator eats the bigger number. Arr, arr, arr. So it's a smaller number eating a bigger number, eating a bigger number. So your biggest thing should be right here in your smallest thing. So following what I have already labeled over here, atomic radius, it tells me the biggest element is over here. Okay, it's increasing. We called it Big Fat France. Big Fat Francium is my biggest element, the biggest volume, biggest atomic radius. So the closer I am to Big Fat France, the bigger I am. I increase following the arrow. So smallest to biggest. Lithium, and then sodium, and then potassium, and then cesium is the biggest because it's right next to Big Fat France. Lithium is the furthest away from it. Do that same process for 24. 25, you're doing the same thing, but they're asking about ionization energy now. And helium has the highest ionization energy. So let's look. Number 25 you should be able to do. Number 26, let's just show you an example. And again, I'm going to use my little pieces of paper right here and say which one has the highest ionization energy. Sodium, that's right there. Neon, that's way over here. Sodium, I'm looking at the wrong problem. Chlorine, right there. Silicon, Si, right here. And magnesium, Mg. So the question says, which one has the highest ionization energy? The biggest ionization energy, if I follow the arrows, is over here. So which one is closest to my big ionization energy? That would be this one right here, which is chlorine, Cl. So these papers are very helpful because they're going to organize your problem, and you don't have to be doing this with your fingers and trying to keep track of what elements we're talking about. 27, go ahead and check your answer. 28, you should be able to do on your own. 29 and 30. A lot of my students skip these problems on the homework, and I told them you have to do those problems. It's going to look like that on your take-home test. If it's on your take-home test, it's on your exam. So losing electrons. Easily losing electrons means you have a low attraction to your own electrons. Do noble gases easily lose electrons? No way. They do not easily lose electrons because they have a very high ionization energy. So that's what we're going to put here, ionization energy. And I would expect you to spell that out. I'm going to abbreviate so I know who's watching this on mute. An atom which strongly attracts electrons in a bond. Okay. So we're talking about an element that wants to gain extra electrons. Do the noble gases want more electrons? No, they don't. They already have 8. So that's why noble gases have no electronegativity. It starts here. So this would be electronegativity. And I'm just going to write En again, just so I know who's watching this on mute. You should spell out electronegativity. Page 3. I'm going to ask you to answer number 31 on your own. Number 32, what are 2 things that are wrong with it? I'm not going to write them out for you, but I highlighted them for you. What's wrong with it? Well, these guys are sharing a bedroom when there's 2 empty rooms in the house. Mom and Dad don't get an office and a gym and make Tommy and Susie share a bedroom if they don't want to. Those kids are going to pitch a fit and ask for their own bedroom. Okay? They're not going to share if they don't have to. And then this electron up here, if there's empty room, that's not in the ground state. So that electron won't go there. It will be down here. So you'd have 1, 2, 3 by themselves, and 4s would be empty. So the first thing wrong with it is you had electrons sharing an orbital when there were empty orbitals. The second thing wrong was you had electrons up here in high energy, but electrons fill low energy first, then to high energy. 33, you can check your work. Nitrogen is in group 15, so it has 5 valence electrons, 1, 2, 3, 4, 5. Filling in your valence electrons for bromine. Bromine is a halogen, which you should know means it's in family 17, which means it's one of the most reactive nonmetals. We should know that from Unit 1. But if it's in family 17, it has 7 valence electrons. So you have to put the first 2 in the S up and then down. In order to share, they must have opposite spin. And then they're each going to get their own orbital. Up, up, up. Okay, so again, it's in group 17, so I need 7 valence electrons. Right now I have 1, 2, 3, 4, 5. Then I can come back and go 6, 7, like that. Now it's bromine. Go ahead and do the same thing for argon. Argon's a noble gas. Number 36. This is a fantastic ACT type of question, and I'm going to highlight it. This question tells you something and asks you something. That's what standardized tests do. ACT, SAT, PSAT, AP tests. They're going to do this. So write on your problems. An atom of fluorine more strongly attracts electrons in a bond compared to an atom of calcium. That is something that I am telling you. And the definition of your answer is right there. This is because fluorine has a higher blank than calcium. Well, there's a couple ways to answer this, but the best way is to say strongly attracting electrons in a bond. It means you are going to get new electrons. Fluorine gains more electrons compared to calcium. Getting new electrons, this is a definition from your notes that you should know, is electronegativity. Okay? Fluorine has a very high electronegativity compared to calcium. Calcium has a very high atomic radius compared to fluorine, but fluorine has its higher electronegativity, which is the ability to attract electrons in a bond. Electronegativity. Number 38. I'm not going to answer for you, but I am going to tell you this. Losing electrons easily. There's your key thing, or being attracted to your own electrons. There's your definition for your answer. So on your test, circle what I tell you. I gave you the definition of which vocab word. There's your take-home test. That's how you're going to do your real test in class. Number 38, you need to know this definition. The old model of matter that we used to use was the Bohr model. Our current model of the atom is called the quantum mechanical model. All right. Explain what an atomic orbital is using terms like 95%, shape, electron, and probability. Remember, so our old model, our Bohr model, is not our current model. But it said, here is a positive nucleus. Here are electrons orbiting it, 2 in this energy level. 1, 2, 3, 4, 5, 6, 7, 8 in this energy level. So the old model said, here's an electron, there's its orbit. It's in this spot, moving just like this all the time. That was the word orbit. The orbital is quantum mechanical update for that. So the quantum mechanical model says that an orbital, like an s orbital, which is the nucleus in the middle, or a p orbital, is a 95% probability of where an electron is. Okay? So 95% of the time, this is the shape where an electron probably is. Again, I'm not going to write that sentence out. I'll say it again. An atomic orbital is the shape which represents the 95% probability of where an electron is located. Because on the other page, on page 1, we talked about the Heisenberg uncertainty principle. We can't know where an electron is and where it's going at the same time. So instead we say this is the shape where it probably is 95% of the time. You do need to know that definition on your take-home test, which means you do need to know it next class. Which of the following can be stopped by clothing or paper? The bigger you are, the more likely you are to get stuck in a strainer. So when you make macaroni and cheese, you pour out your noodles into a strainer. Noodles get stuck, can't fit through the strainer. Big fat alpha particles, right, 4,2He, they get stuck by paper because they're too big, which means they're not very dangerous. They can't get into your skin. They can't hurt your DNA. Take a look at these two then. Stopped by lead and thick concrete, and which one's the most harmful to our cells? Go ahead and answer those ones. Check your nuclear foldable if you're not quite sure, but make sure if it's on the take-home test, you have it memorized for next time. All right, let's get into some nuclear chemistry. Balance the following nuclear reactions. Here you are to check your work, and I showed you what I did here. Okay, So I have plutonium reacts to form uranium and an alpha particle. I knew this was an alpha particle because I said the top numbers, 244, has to equal 240 plus x. And in solving for x, I found that x equals 4. Okay, 244 minus 240 equals x. 240 plus 4 equals 244. Our bottom numbers, 94 equals 92 plus something. So if I used to have 94 protons, and now I only have 92, it's because I spit out 2 of them, x equals 2. And if I write the number 2 right here, that means the symbol is He. Atomic number 2 has the symbol of He, 42He. Number 44 is beta decay. I know it's beta because it's written right there. Alright, that's how I would know that. Let me grab your test copy of the periodic table. Your test copy of the periodic table will have that information. So this will be the front of your periodic table, and on the back side, you have a section called nuclear. It tells you what an alpha particle is, that this is a beta particle, that this is a symbol for neutron. Okay? So I know this is beta decay, which means I have 138 on top equals something plus 0. Well, in order to make this equal, 0 plus 138 is 138. Okay? So for the bottom, I've got 53 equals blank plus negative 1. Okay? So some number minus 1 equals 53. So what I need to do to solve for x is to add 1 to both sides. Okay, because right now I'm subtracting 1. So to cancel that out, I add 1 to both sides. 54 minus 1 equals 53. And element 54 on the periodic table is xenon, Xe. Okay. 45 is the same thing. It's still beta decay, but instead you're solving for the unknown reactant, not the unknown product after the reaction, but the unknown reactant. So what I have here, and I'm going to do it in a different color just so that I can keep it straight from 44, is to say that some number here on top, x, equals 11 plus 0. Well, 11 plus 0 is 11. I'm going to write 11 there. And then on the bottom, some number, x, equals 6 plus negative 1. Okay. Now for some of your algebra brains, you know that adding a negative number is the same thing as subtracting. If your brain doesn't do that very easily, and you can stick this in your calculator, you don't get points for doing it mental math, right? 6 plus negative 1 equals 5. Okay? And that makes sense if we think 5 equals 6 only if I subtract 1. So there's a lot of ways to kind of conceptualize that, and we worked really hard on that in class. Number 5 on the periodic table is boron. So B. Alright, go ahead and try 46 on your own. On our next page, 47, we're doing the same thing, but now it's a multiple choice format. Okay, because it's a take-home test. It's going to look like your test. I start with plutonium-244. It reacts to form uranium-240. What came out of it? Okay, so 244 equals 240 plus something. Okay, so what number? If my mass went down to 240, it's because I stuck out 4. If I used to have 94 protons and now I only have 92, then I had to have lost 2, which means it's an alpha particle, 42He. One symbol for a beta particle. For crying out loud, this will be on your periodic table if you remember to look for it. And if you are watching this video, you deserve to know this. Okay? Here's your test copy of the periodic table. On the back, it is written right there that a beta particle is like this. A beta particle also looks like this, capital B for beta. Excuse me, I'm answering this on the wrong problem. This is 48. Okay. 48 beta particle right here. And beta also looks like that, but that wasn't one of your choices. So, just the one that's written on the periodic table. Alright, the answer is not A for 49. So find the one that's alpha particle for 49 on your own, and it's right on the screen in 3, 2, 1. Alright, rewind if you need to, otherwise check your notes. For number 50, what does the symbol X represent? Okay, it's the same thing that we did, but now it's multiple choice. So 154 equals something plus 4. Which one of these would complete that problem? Bottom number, 61 equals something plus 2. What number plus 2 is going to give me 61? Alright, so my numbers should be 154 equals x plus 4. So x in this case would be 150. Okay, so I can come through my answers like this. It's not 154. It is 150. It is 150. It's not 158. Okay, because 150 plus 4 is 154. So it's one of these two. The bottom, 61 equals something plus 2. Well, 59 plus 2 equals 61. So both of those numbers are right. 150, 59, B and C both look right. Now we need to look at our periodic table and figure out what element is 59. 59, number 59 is PR. PM is element 61. If now I have 61 protons, I'm PM. If I have 59 protons, I cannot be PM anymore. That's not possible. PM can only have 61. So 59 protons is PR. Then it's asking you 51. It's asking you what kind of decay is this? And by looking at this problem, figure out which particle you have in here. If it's alpha, beta, gamma, or a neutron, which one's in there, and then that's going to be your answer. Okay. Same thing for 52. You're going to solve it just like you did for this one, where you're finding what's missing, but then instead of saying 42He or 0, -1E, you're going to say alpha, beta, or gamma for number 52. Number 53, you can check your answer right there. Fission, Fission, is what I do on Earth with uranium. It is taking a big uranium atom and splitting the nucleus into smaller atoms. Number 53, I'm not going to give you your how do you know. I expect a full sentence for each of these answers, 53, 54. But Fission is what I do with uranium. I take a big atom and I split it up. So this would be fission. For number 54, fusion, Fusion, has the letters SUN in it, because it's what happens in the sun. Okay, the sun takes hydrogen plus hydrogen and makes helium. So this is helium fusion. Okay, I want you to be able to check your answers. So fission is the reaction of atomic bombs. Fission, 2 I's is what I do with uranium on Earth. So atomic bombs is what I do, fission. Alright. The reaction that occurs within stars or the sun is SUN, fusion. Number 57. Combining atomic nuclei. Taking two different nuclei, two different nucleuses, and making one is fusion. You're fusing it together. The splitting up of an atomic nucleus into smaller things. The splitting up of a nucleus. Fission. Okay, please make sure you don't flip-flop those. That would be very unfortunate. Put the following orders, radioactive elements, in order from least penetrating to most penetrating. If it cannot penetrate your skin, it's not dangerous. So it's basically least dangerous to most dangerous, and that would be alpha is the safest. Alpha particles, then beta particles, then gamma particles. Because alpha particles are the biggest, they can't get through your skin. Gamma particles don't have any mass, and so they can get through your skin and mess up your DNA. Alright, question like this one, number 60, is the exact same as these questions up here. The only difference is, up here, I gave you two of the things, and I'm asking you for the third. Down here in question 60, I only gave you one of the things, and you need to find both. But I do tell you it's alpha decay. So one of them is going to be an alpha particle, which is 42He. Miss Holm, what if I don't have that memorized? Well, here it is on the back of your periodic table. Alpha particle, 42He. Make sure you look for it, test day. Then you're going to solve for the missing particle, just like we were doing above. If you are still watching this video tutorial, there's a good chance I'm going to give you some extra credit. Okay? So please box in page 4 and put stars on either side of it so that I know that you are doing your very best on this take-home test to be ready for your exam. Well done. Okay, question 61. If silicon-29 undergoes beta decay, what will it become? Well, yikes. I didn't give you any of this problem. On this side, I gave you almost the whole problem, and you're just solving for one part. On this side, I'm expecting a little bit more from you. I didn't give you any of the problem. You have to write it yourself. So silicon-29, remember, this is always the mass. So I can write silicon has a mass number of 29. I'll look it up in the periodic table. It's atomic number 14. So it's undergoing beta decay, so there's my beta particle, plus what? Whew, that is a hard problem, because you need to write it and then solve it. So 29 equals 0 plus 29. 14 equals negative 1 plus 15. 15 minus 1 is 14. And element 15 on the periodic table is phosphorus, P. Okay? So 2915, yes. 2914, no. 2912, no. 2512, no. 2915, yes. So A and D both have the same number, but number 15 isn't silicon. Only number 14 is silicon. Number 15 is phosphorus, so D. Okay? That's going to be one of the hardest problems on this take-home test. 62, you're going to do this same way. You need to write out hydrogen 3, mass of 3, atomic number of hydrogen, and the symbol. And then write a beta particle and fill in the blank. Question 63, same thing, carbon 14. So it's going to be carbon with 14 on top, and then carbon's atomic number reacts to an alpha particle plus something. 64, an isotope of plutonium-239 will have. This is very much a review from Unit 1, and it's Ape Man. You should know Ape Man by now. Atomic equals protons equals electrons. Mass minus atomic equals neutrons. So atomic, 94, that's the bottom number, the subscript, equals protons and electrons. So my protons need to be 94, and my electrons do too. So A looks good. I'm just going to underline those so I know that they're good. 94 and 239, no way. Protons have to equal electrons while they're neutral. B, 94 protons, 94 electrons, that looks good. 94, 145, no way. Okay? So now I've got this narrowed down to either A or B. Man, this top number is the mass number. It is not the number of neutrons. That's the total mass. So mass minus atomic. Let's do that in a calculator. 239 minus 94, 145. Okay. The top number, the superscript, is the mass. The bottom number is the atomic number. All right, and that's pure review from Unit 1. Go ahead and check your work on number 6. For these next 4 problems, our last 4 problems, you're going to need this graph, and you'll have it. You should plot these points on your own. So number 66 is the same thing we were doing up here, but a step further, a step harder. An atom of the isotope 7730 zinc will likely have, the first thing I ask you is neutrons, so we have to solve for that. Mass minus atomic equals neutrons. So 77, my mass number, let me clear that, minus 30 equals 47 neutrons. Okay, so yes, that one looks fine. That one looks fine. 30 neutrons, no. Okay, next I need to graph it. I have 47 neutrons. 47 is right about here. Okay, excuse me, no that's not. That's 67. 40, so it's 0, 10. 20, 30, 40, 50. So 47 is right about here, 47 neutrons with 30 protons, which is right here. I'm going to graph this point right here. I'm going to pull this up. Okay, 47 neutrons and 30 protons. That's in the light gray. That would be unstable. So it is not a stable isotope. That would be a radioactive isotope. Check your answer only on 67. Number 68. I want you to do the same way that we did this. So go ahead and do that the same way. 69 says the element tellurium has 52 protons. Could stable isotopes of tellurium exist? And that's tellurium, Te. Could it exist? It's not too big. Once you're over about 85 protons, then you're too big. Because up here, with 85 protons, there's no more dark gray. There's no more stable isotopes. So it's not that it's too big. 52 protons, if this is 50 and this is 52, I can pull it over and say, right in this region it looks pretty stable, between here and here. Which if I pull that down between here and here, it looks pretty stable right there, which is about 68 to 75, somewhere in there. So for this one, yes, with about 52 neutrons. Well, with 52 neutrons, that would be unstable up here. So it's not A. Yes, with about 68 neutrons. Yeah, 68 would be right about here. That point would be right about there. That looks pretty good. I don't circle it, I still look. Yes, with about 80 neutrons right here. Okay, that looks unstable to me. So I'd say C, about 68 neutrons. On the back, we completed this in class. So you should have this completed from your class notes. If you were absent, you'll have to talk to your teacher about making that up. Alright, if you did great on this take-home test, and you understood it, you didn't just copy, you should do really, really well in our exam. Good luck.